Hi there, welcome to this calculus tutorial. Today we're going to talk about evaluating integrals using partial fractions. So we use this when we have something that's too complicated to integrate on its own, so we simplify it into separate partial fractions that are easier to integrate individually. So say we are given a problem like this. Well, the first thing I would want to do is factor as far as I can that denominator. And so I go ahead and I can do this with either polynomial long division or synthetic division, and I get x plus 1 times x squared plus 1. And once I have it in this form, I can no longer factor any farther, so I'm stuck. So now I check, can I solve this with partial fractions? And the answer is yes, I can. So I've provided a table over here on the right to help you figure out which partial fractions to use depending on your factors in the denominator. So it looks like I have something similar to this, an x minus a times an x squared plus bx plus c. Now I don't have a b term in my case, but it's still in this general form. So this is the partial fraction decomposition that I'll use to simplify this. And once I have that, I've solved my a, my b, and my c. I'll go ahead and integrate each of those fractions separately to go ahead and get the final answer. So I go off to the side and I do a little bit of extra legwork. So my 4x over my factored form of the denominator will then be equal to my partial fractions. So I take a over x plus 1 and then bx plus c over the x squared plus 1. And my goal then is to solve for a and b and c. And when I do that, I can then integrate this form to get my final answer. So what we need to do is we need to find a common denominator. So I multiply both sides here by x squared plus 1, and I multiply both sides over here by x plus 1. And then I can go ahead and I can distribute, and I can get a common denominator. And once I have that, I can go ahead and I can add those two fractions together. The left side, as you see, stays the same. And then the right side, I'm going to add them all over the same common denominator. So I end up getting all of this over x squared plus 1 times x plus 1. All right, so now you can see that these denominators will cancel each other out, and it simplifies down. And I can go ahead and I can distribute that a, and I can FOIL out this second part here. So I end up with bx squared plus bx plus cx plus c. And then I can go ahead and I can group like terms. So the left-hand side stays the same, and I end up with a plus b x squared. Those are my x squared terms. I end up with b plus c are my x terms. That takes care of my x terms. And then a plus c are my number terms. And then I go ahead and I compare to my left side. So this would be the same as saying I have 0x squared plus 4x plus 0 equals this. So when I go ahead, I can bring down the 0 equals a plus b. That's my x squared term. The 4 equals b plus c. That's my x term. And then 0 equals a plus c. That's my number term. So I compared each of the coefficients on the left side and set them equal to the coefficients over on the right side. So now I have a system of equations that I can go ahead and solve. So I see here that a equals negative b. So if I plug that in over here, I see a equals negative c, which tells me then that b must also equal c. And when I come over here, I see that c equals 4 minus b. So I can plug this in. b equals 4 minus b. When I add this over, I end up getting b equals 2. So that's one of my coefficients. When I plug that in here, I get c also equals 2. And then when I plug that in here, I get a equals negative 2. So now I have all three of my a, b, and c factors that I need to go here in my equation. So now I can go ahead and I can rewrite my integral in a little bit simpler form. So I'm going to take this, and I'm going to rewrite it down here. And so this new integral becomes negative 2 over x plus 1. I just substituted in what I found for a. And then my b here is 2x plus c was 2 over my x squared plus 1. And now we see here, if we have two things that are being added in the numerator, I can split these up over that same denominator. So I'm going to expand this one more step. I have negative 2 over x plus 1, that stays the same. I'll have 2x over x squared plus 1, and then 2 over x squared plus 1. It's like doing a reverse common denominator. So now I have three separate fractions that are equivalent to what I started with. And this looks simpler to integrate. We know how to integrate each of these things. So that first term becomes negative 2 ln of x plus 1. That second term becomes ln of x squared plus 1. And then that last term becomes 2 times the inverse tangent of just simply x. And then because we didn't have a definite integral, we must add a constant. And that, my friends, is your final answer when you solve this integral using partial fractions. Follow the same process every time you're doing an integral with partial fractions, and you'll get the right answer every time. Good luck!